Hello and welcome to Microsoft Ignite here in Orlando. My name's Dean Bryan and I'm a cloud advocate here at Microsoft, and in this session we're going to be talking about preparing for growth, capacity planning and technically scaling our applications in the cloud. Before we get started, I wanted to share with you a number of resources. There's a link there to the resources specifically for this session. There's also some of the code on GitHub for any demonstrations that we performed during this session. And then alternatively, there's also all of the event sessions from all of the Microsoft Ignite here in Orlando over at that short link you see there at the bottom. So let's get started. For this learning path, and if you haven't been in any of the sessions in this learning path already, we're going to give you a map that will not only help you know what things you can focus on to improve reliability, but also the most effective order for these steps. The map for this learning path is based on something from the site reliability engineering world called the Dickerson hierarchy of reliability. Mikey Dickerson created this hierarchy while he was facing one of the largest reliability crises he'd ever been asked to address. And it's a riff on Maslow's hierarchy of needs. Just like Maslow's hierarchy, the idea is that there are a set of levels for us to progress up the pyramid. We need to make sure that all of the lower levels are solid first. So the levels in this hierarchy consist of monitoring, responding to incidents, learning from those incidents, creating processes that help you avoid incidents before they happen, and finally, dealing with growth, because success can really threaten reliability just as much as failures can. Dickerson does suggest two more layers, the development process and the user experience aspects, but we won't cover those in this learning path. And so welcome to the Ops learning path. Each of the sessions in this learning path are aligned to one of the parts of the pyramid, and this particular session will specifically be looking at capacity and scale. So to set the scene, we're dealing with Tailwind Traders, this company that you've all become familiar with over the session, no doubt. And they've got a big event coming up. They've got a new product launching soon. It's the revolutionary electric hammer. It's going to be a roaring success, and nobody except for Homer Simpson, of course, has ever launched the electric hammer to the masses. So they're expecting thousands of new users to come and hit their site. But obviously they want to make sure that if you've seen any of the sessions already, the Tailwind Traders architecture might not be exactly perfect. And we don't want to leave us like poor Bit the raccoon here, stuck in the middle of a load of flames, pretending that everything's okay, when really everything is burning down around us. So we should prepare and plan for the growth that we're expecting for this new product launch. And how do we do that? Well, first of all, I want to look at some of the single points of failure within the Tailwind Traders architecture. All of these services here where you see the fireball are not built for resiliency or for scale. If one of them got overloaded, it's likely to crash. And there's no really easy way to solve that at the moment. So one thing we'll look at in this session is how we could design these services to be more scalable and more reliable technically. A few other services indicated by the cross here is that they need pre-provisioned capacity. If we exceed the limits that we've provisioned for these services, we're going to start returning error messages to our customers. For Cosmos DB here, for example, we pre-provision the throughput. With cognitive services, we select the tier, and that tier has a maximum number of requests per second. Once we hit either of these, client requests are going to be throttled. Will the product launch make us hit these limits that we've pre-provisioned? Right now, we just don't know. So that's another thing that we're going to have to figure out. And we even need to plan for growth when we've done stuff right. Here you can see where the money bags are. We're using Logic Apps and Azure Functions. They're both examples of serverless technology. This means that these services scale automatically and we only pay per request, which is brilliant, but we are paying per use here, which is also great. Your bill grows just as your customer base does. So what's the catch? Well, we should at least be aware of the impact that this upcoming event may have on our cloud costs. So that's another thing we'll look at in this session, understanding and predicting our cloud costs. So there's a lot of things for us to look at in the Tailwind Traders engineering team. We've certainly got our work cut out. And hopefully these sound like challenges or questions that you've had to deal with in your day jobs too. So let's dive into how you can prepare for growth, as well as seeing how we can make our products more scalable and reliable in Azure. First, let's talk about scaling and when we may need to scale. Sometimes we can plan for scale. Maybe there's an upcoming sale event, on our e-commerce website, or we've got a big launch coming up, just like the electric hammer. Sometimes we don't have the privilege of any prior notice. Maybe a celebrity has endorsed your product, or worse, you've been hit by a distributed denial of service attack. Hopefully, if either of these happen, we don't need to have any human intervention, and the system gracefully handles a new load. But we all know that this nirvana is very rarely, if not ever, possible for complex distributed systems that we have today. So we're going to look at how we can plan for scale in all three of these scenarios. And just a quick primer here, I want to give you some prerequisites for this session. From now on this session, I will expect some prerequisite knowledge of scaling. So I want you to understand the difference between scaling up and scaling out before we go ahead. Either getting a bigger instance versus adding more resources. I also want you to know the difference between manually scaling, where we have to manually go in and turn up the dial, versus auto scaling, where we configure our systems to scale automatically. And slightly similar, I want you to know the difference between DIY scale and inherent scale. So do-it-yourself scale is even auto scaling, really. We have to go in and configure the auto scaling ourselves. Whereas some services, such as Azure Blob Service, are inherently scalable. We've built them to be scalable, and you don't need to worry about them at all. If you're not familiar with these terms, then this session might not be for you, and you should maybe check out some of the awesome content over in the fundamentals track. Alternatively, there's a whole ton of great content on these topics in the Azure Architecture Center at the link there. But hopefully I've still got you, so let's go. I want to kick this off by just highlighting that making our app more scalable also makes your app more reliable. For example, if your system auto-scales, then given a component failure on a single machine, the auto-scaling service will provision another to meet your minimum virtual machine count requirements, meaning you're instantly more reliable too. Likewise, if you're leveraging higher level services or inherently scalable services such as Azure Storage, we've also built them to be reliable under the hood, so data is replicated, etc. One good analogy is these accessibility ramps you often see outside of buildings. They were initially designed to help those with wheelchairs. A secondary benefit, however, was that they also help parents with pushchairs. This is how I like to think of scalability and reliability. If we design our systems to be scalable, the secondary benefit is that they'll likely be more reliable too. So how do we plan for growth within the cloud? Well, the first question I always get asked is, we're using the cloud, right? It's got infinite scale. Well, yes, there probably is enough scale in the cloud to meet your application's demands, but we still need to understand our capacity needs for a couple of reasons. Firstly, we need to think about our forecasted cloud spend for our friends in finance, and we'll cover more on that shortly. Secondly, although there is likely enough resources in the cloud, not all of the services we consume scale automatically, so you need to be aware when you're going to have to scale things up, or even hit soft service limits that are imposed by the cloud provider. So how do we capacity plan in the cloud? Let's take a look at that Tailwind Traders architecture again. The first thing we should do when looking to capacity plan in the cloud is to map out all of the current resource requirements for the larger components in our application. In this example, it could be that Azure Kubernetes Service Cluster, maybe our rewards app running in App Service, or our various databases, Cosmos DB, Azure SQL, and the like. And then for each of these large components, we need to understand what the current resource usage is. This will help us plan for future usage. Now, I'd love to cover all of those during this session today, but unfortunately we can't. So I'm going to focus on one particular one, which is Azure Cosmos DB database. Before we look at the resource usage of our Azure Cosmos DB database, we need to understand how we measure capacity in Cosmos DB. Storage is measured in gigabytes used, and it scales automatically for you. You don't need to worry about that at all, so that's pretty simple. Throughput, however, is pre-provisioned. We use a metric called request units to measure this. Request units are a mixture of memory, CPU, and IOPS to give you a single metric to plan capacity by. You provision request units in increments of 100 request units per second. Every single operation on our database is measured in request units. As you can see here, reads are simple. A 1 kilobyte read is a single request unit. Other operations are calculated based on a number of factors, such as item size, data consistency, query patterns, etc. Now, it may seem confusing, but when you're profiling your application, every single response you ever get from Cosmos DB contains the request charge header, and this tells you exactly how many request units have been used. So you can use this to profile your application. So let's go and have a look at how we can go into Azure Monitor and retrieve capacity metrics for our Cosmos DB database. So here I am in the Azure portal. I'm going to search for Monitor in the top there and select the Azure Monitor service. What we care about here is metrics. We want to look at the resource metrics for our particular service. So once this system is loaded, we're going to select a resource. We can filter by resource group, and we can even search by text to find the name there. We're then going to look specifically for our Cosmos DB account, which we found there, and we're going to hit apply. We can then go and select the metric, and in this case we're going to look at provisioned throughput. This is going to tell us that we have 1,000 request units provisioned in our database. We're then going to add another metric, and it handily copies over the same resource. And on this one we're going to pick total request units and look at the average. Now you can see this is quite comical. We're currently using about 4 request units per second, and we've got about 1,000 request units per second provisioned. So we can tell by looking at this graph that we have more than enough capacity to see the growth through our system. So actually in this scenario we could actually scale down our Cosmos DB provision throughput if we wanted to something a little bit more realistic, because don't forget, when things are pre-provisioned we're already paying for them. Now that was a pretty simple example, and the request usage there isn't really realistic. So let's look at a hypothetical example of Tailwind Traders usage coming up to the launch of the electric hammer. So in this example here, Tailwind Traders are growing at an average of 2,500 monthly active users, with a current user base of around 10,000 users. Now you may wonder why I'm looking at users here. Well, it's always good to correlate our resource usage to a business metric such as monthly active users or revenue, etc. This helps us plan our capacity based on how we expect our business to grow. If we can correlate our business metric to our actual resource usage, we can extrapolate that for known growth events such as the launch of a new product to try and plan what our capacity needs may be for that event. So we see we're growing nicely, about 2,500 users per month here. If we look at storage, we can see that each month our database is growing at around 1%, or 50 gigabytes per month, and we're using about 300 gigabytes of 5 terabytes available here. As I said earlier, our storage scales automatically, so we can ignore those higher limits. Cosmos DB will take care of that for us, but we do want to know about our storage growth for cost reasons. And we can also see here that our throughput, our request units, is sitting at 300 request units out of 1,000 request units, and that's growing at a rate of around 10%, or 100 request units per month. Understanding our system's resource metrics like this means that we know when we're likely going to have to scale our throughput, and also what our cost will be over time. For example, we now know that in June we're going to reach capacity of request units on our database, so we'll need to scale before then. One other interesting insight, as I mentioned earlier, is that for now we could maybe even scale down our Cosmos DB database, as we aren't using anywhere near the pre-provisioned capacity. So we need to work out here in this graph that maybe around the March or February time we need to start looking to increase the pre-provisioned throughput of our Cosmos DB database. Now I must highlight here that actually at this conference here at Ignite we launched something called Autopilot for Cosmos DB, which enables you to auto scale, so you don't have to care as much about pre-provisioned throughput. But one thing you do need to be aware of is that there is a maximum limit that you configure, and it scales down to 10% of that maximum limit. So you need to still be aware, just in case you hit that maximum provisioned limit that you've set, that you may need to still capacity plan and increase that maximum limit when you start getting near that point. So this is how we can plan for organic growth, right? We're looking at organically, we're growing 2,500 users a month. That roughly works out to 50 gigabytes of storage and 100 request units. But what about inorganic growth? Sometimes we really don't know about an increase in traffic or users. In these cases, we need to build our systems to be as scalable as possible automatically, and to fail gracefully when that isn't possible. That's going to be the next part of the session. But sometimes, just like the upcoming product launch of the electric hammer, we experience inorganic growth that we can prepare for. If we work together across engineering, product, marketing, and finance, then given resource usage and growth patterns that we just obtained, we can try our best to predict the impact of these events on our resource requirements, and we can implement the changes we need accordingly. Getting this right is a bit of a dark art and will likely be specific to your organisation and the particular event. We won't always get it right, but being as prepared as we can be will give us a head start. Let's look at an example for Tailwind Traders. So let's say, for example, there's an upcoming marketing event. In our case, this is the launch of the electric hammer. And we're expecting that that's going to drive 5,000 more users to the site. If we use the data that we obtained from our previous example of organic growth, and we correlate that, hopefully with some causation, to a business metric we have from our product or marketing teams, number of users in our scenario, we can start to plan for inorganic growth events. We know from beforehand that 2,500 users equals about 50 gigabytes of storage, and we also know that that equates to around 100 request units. So we see in this event that we're expecting 5,000 more users to the site. So we can see the math there that we can expect around 100 gigabytes of extra storage and about 200 request units. So let's use that data to go and see if our system, particularly our Cosmos DB database, is ready for this launch event. Here for storage, we can see that our storage capacities are more than sufficient for the growth expected in the event. This also scales automatically for us, so we don't really have to have any worry here except for understanding our new costs, which we'll get to shortly. We can also predict that our request units will only reach 50% capacity following the event, so we're all good. So we know that for Cosmos DB, we've got sufficient capacity for this particular scaling event. But what about the cost? We can see here that the 100 gigabytes of extra storage is going to cost us an additional $25 per month on the left-hand side of the graph there. Our throughput costs stay the same. This is because we pay for pre-provisioned request units, and we already have that 1,000 request units, which is more than enough. Meaning that this marketing event is likely to increase our Azure bill, particularly for Cosmos DB, by $25 US. So here we're understanding what the cost will be after the event. So it's a rough idea of how we can plan for inorganic scaling events like product launches by working closely with our business and finance and product teams as engineers. But capacity planning also involves understanding when we're going to reach and hit service limits. When looking at your system and its architecture, you need to understand the limits for the cloud services that you're using. For example, by default, you can have a maximum of 200 virtual machines per VM availability set. This may seem like a ton of virtual machines if you're just getting started out, but just be aware that when you hit that limit, you're not going to be able to provision any more, which could potentially result in an outage. Likewise, by default, you can have 250 storage account per subscription per region. These are both examples of soft limits that can be increased, but some services do also have maximum hard limits as well, which you can find at the link there of aka.ms/OPS50 limits. It's just something to be aware of and keep your eye on, and there's a couple of ways in which you can do that. First, we can see in the Azure portal, we head over to the subscription area, and then on the left there, we can click usage and quotas. You can filter on service categories such as network and compute, as well as the Azure region. It will show you where you are against the current limits, but sometimes you might want to check this programmatically too. Each Azure service has a list usages API endpoint. Here is a truncated example of the list usage endpoint for Azure Virtual Networks. You can see here that the current number of VNets being used is 124 against a limit of 1,000. Now you can increase these limits, but they will require a support request, so make sure that you know ahead of time when you're going to reach these limits. So either keep an eye on that chart in the portal or programmatically hit the list usages API so you know when you're going to hit these limits. Now let's talk about cost. It's easy for me to stand here in a scaling talk and tell you that to scale, you just need to throw a whole ton of resources at the problem. But it's very important as an organization to understand the cost of your cloud environment, and that adding more resources generally equals more cost. So be aware of that and work with your finance teams to ensure that you're in agreement about current and projected cloud spend. You should forecast for cost when both initially designing a system and also for existing running systems up in the cloud. Azure gives you some tooling to help you understand this. Let's have a look at what that is. So here I am in my browser, and what I'm going to do is look at how we can plan for a new system we're running in the cloud. So I'll navigate over to the Azure pricing calculator. aka.ms/Azure calculator is the short link there. Now within this pricing calculator, I can start adding the various components of a proposed architecture, and it will show them up as line items in this particular page, and I can save the estimate, download it and share it with my colleagues. So if I click virtual machines here, you'll see that's been added to my bill. I can select the region, I can look at the operating system, the type of operating system, Linux, Windows, and also the variant, as well as the various tiers and the types of virtual machines that are available to me. If I pick this D4SV3 virtual machine here, you'll see that the price will be updated and reflected as $170 per month. I can also select to reserve that for a number of years and select savings. So I can, within the calculator, I can take into account some payment mechanisms that I have available to me. I can go ahead and add all of the components of this particular architecture or this particular system here, which will give me a rough idea of what my cost will be going into a new system, so we can just plan for the future in terms of cost. But what if we've already got something running in the cloud? Well, if that's the case, we can head over to the Azure portal. We can go to subscriptions in all services here. We'll click into that, pick my particular subscription that I'm using here, and you'll see that in the front pane there, we've got a rough pie chart showing us what our costs are based on resources that we've got. You see I've got some there that are costing me a few $100s. And if we go into cost analysis on the left hand side there, I can start looking a little bit more detail about what my costs are. So we'll look at current trends and accumulated costs. And here it gives you a nice graphical representation of what my actual current cost is, as well as what my forecasted cost is for the particular month. So here I have $672 I'm spending, and I'm forecasted to spend $2,806. Please don't tell my boss that if anybody is watching. I've gone way over my monthly budget of $1,000 per month here. But we'll talk about budgets in a moment and how we can set particular budgets for our resources. And then you get this nice colourful graph showing you when you're going to reach your particular limit and against your budget in a nice green and red way, so you can really see how things are planning out. Now, if anybody's used Power BI, these graphs at the bottom here, if you click into one of them, it will readjust the whole chart to reflect that specific element. So I can select a resource group or a location or a particular service name to see to filter down the graph a little bit as well. You see I have a resource group here called Love Island, which is attributed into about a quarter of the spend within this resource group. I've also got another one there very similar called TWT for Tailwind Traders. And I can click into one of these and see particularly what services are costing the most money. So in this particular example, once it loads, you can see that actually 50% of my cost for that resource group is coming from a Redis cache. Now, this may be expected behavior. This may be something that I'm fully aware of, and it's something that's okay, but it still helps us identify anomalies to see if there's anything that we need to start diving into and looking at to understand the cost of our resources. Now, as I mentioned earlier, there is a budget there of $1,000 per month. So you can actually go and set a number of different budgets in different ways based on various scopes and various resources that you've got as well. If you click on budgets in the left hand side here, that will take you into the budget pane, and you can see that I've got a budget here once it loads of called monthly spend. So if we click into that, we can see the details. I've called it monthly spend. My limit is $1,000. The budget period resets monthly, so I've set that for the starting in the month of September and then going through to an end date of 2021. And I can also set at the bottom some alert conditions. So I've got here an alert that says if I reach 90% of that budget, or $900, I want to trigger an action group. In this case, this group that I've set up here sends an email to myself to let me know that I've hit 90% of my budget. So I just know ahead of time what my budget is and when I'm going to hit that as well. So we've had a look at how we can plan for scale in terms of cost, provisioning our resources, looking at what our resource usage is, and making sure we're aware of our cloud service limits. But how can we technically make our application more scalable? One thing I want to firstly emphasize is that you should perform regular architectural reviews of your systems. As you learned in the previous session in OPS50, we can leverage practices such as infrastructure as code to improve how we deploy our cloud resources. While we update and improve our application code, and our developers do that regularly, we should do the same with our underlying platform resources and our cloud architectures too. And performing an architectural review of our system helps us identify any areas for improvement. It helps us understand what new services have been launched, if there's anything we should change, if there's any way we can make something more scalable or more reliable. The Azure Architecture Center has a wealth of resources to help you architect your application in the cloud. There's a number of scalability recommendations, particularly that you can find in the application architecture guide at the link that you see here on the slide. As I mentioned earlier when we spoke about cost, throwing resources at things might solve the problem, but it will cost you. So as a technical team, during those architectural reviews, you should find the bugs first before scaling out your resources. Now, what do I mean by that? Well, some examples. You might have a badly designed database. You could have hot partitions in a NoSQL data store. If you're only using one partition on a huge NoSQL database, it's going to be slow, no matter how big you scale and how many resources you throw at it. If you've got inefficient database queries, can you make them more performant before you go ahead and just scale the database and throw more resources at it? Is your developer's code inefficient? Is there a way that we could write more efficient code for your application? Are your timeouts set correctly? Are your database connections getting saturated due to reties from inconsistent timeouts between the server and the database? These are things that you can go and check during those architectural reviews that you can fix and improve the performance of your systems before having to throw more resources at. And one final thing to bear in mind as we dive into how we scale technically. You'll notice that the changes we speak about here often have dependencies on the developers of our applications. And that's right. Some of these suggestions and best practices will require collaboration between you and the developers to make it happen. And although you might not be able to implement these changes entirely by yourself, understanding the cloud system and its capabilities and characteristics can help you be the driver for change in improving your systems and their scalability. So let's look at how we may take our Tailwind Traders application and make it more scalable. Just looping back to that architecture again. I want to highlight what's good about it before we kind of break it apart and find all the flaws in it. Firstly, you can see that we've decomposed our application into smaller microservices. Some of those are sitting as containers on Azure Kubernetes service. They could just as easily be running on virtual machines or app service. We're also using some inherently scalable services, such as Azure Functions and Logic Apps. But there are definitely some improvements that we could make if we want to be more scalable. So how do we approach that? I want to focus on one service, that product service that we are having some difficulty with and it's not scaling very well. It keeps using and exhausting all of its resources and falling over. So we can probably fix this. It's a single point of failure. It doesn't scale very well. It keeps falling over. How can we take that product application and make it a little bit more scalable? Now, this is demonstrated here as a single virtual machine connected to a single Azure SQL database. The reason that I've done this is because I don't want to assume any prior knowledge of containers or Kubernetes in the audience. So although in the wider diagram that we just saw, this is a pod or a node within Kubernetes cluster, in this particular walkthrough, we're going to look at it from the concept of a virtual machine. So I don't expect any prior knowledge of containers going forward. So as I said, we've got a single virtual machine connected to a single Azure SQL database in a single availability zone. What we really need to do to enable this to scale first is to enable virtual machine scale out. Give us the ability to add more virtual machines to our server so that we can handle more resources. And what can help us here is that we can use virtual machine scale sets. Azure Virtual Machine Scale Sets lets you create and manage a group of identically load balanced virtual machines. Yes, the load balancer. Now we have more than one virtual machine, we're going to need to introduce a load balancer to distribute traffic across the virtual machines. By leveraging virtual machine scale sets over a single virtual machine, we get a few benefits. With scale sets, we can auto-scale based on host metrics, in-guest metrics, application insights or Azure Monitor metrics that we saw earlier, or by schedule. It also enables us to leverage availability zones. Availability zones are independent standalone data centers within an Azure region. With availability zone support, it means we can spread our virtual machines across multiple availability zones, which will make it more reliable and protect us from data center failures. New instances within a scale set will automatically be evenly distributed across availability zones. And adding that load balancer becomes easy too. Virtual Machine Scale Set supports the use of Azure Load Balancer for basic Layer 4 traffic distribution and Azure Application Gateway for more advanced Layer 7 traffic distribution and SSL termination. In order to implement scale sets, your application must be able to scale out. So before you go ahead and do this, you must make sure that you avoid instance stickiness and no client is being stuck to a specific backend. You remove any persistent data from the virtual machine and store it somewhere else, such as Azure Storage, in a database or a Redis cache or something like that. And it's also important that your application can also easily handle scaling back down. This is just as important as scaling up, and this is often overlooked. So we've added some more virtual machines with scale sets, and scaling out is that typical answer to we need to scale. But we can only scale here really on a single metric. This might not be relevant to all tasks being performed by our product service. In fact, in Tailwind Traders, it turns out that our product service has a job. It takes an image, and once that image has been uploaded, it transcodes that image and stores it in a number of different sizes for thumbnails and pictures in the catalog, etc. The image processing process is pretty CPU intensive, but the general usage of the product service is memory intensive. This is an asynchronous task that can be broken down into a background job. We can do that by decoupling our imaging process service via a queue. This means that we can scale both services independently, one on memory, the product service, and the other, our image processing service, on CPU, or even something like queue length, and have another scale set consume those messages and process the images. So let's look at how we could scale via queues. In Azure, we have two types of queue offerings. We have Azure Service Bus queues, which is a more advanced queue offering. It's part of the broader Azure Service Bus product, offering pub sub and some more advanced integration patterns. Azure Storage Queues is the alternative. This is a simple REST-based queue interface built on top of Azure Storage, offering reliable, persistent messaging. Our requirements here are super simple, so we'll be using Azure Storage Queues in this demo. Let's go ahead and have a look. Here I am in the Azure portal. I'm going to go ahead and type in the top here scale sets, and this will take me to my virtual machine scale sets. You can see here that I've got a scale set at the top, and if we click on instances in here, we'll see that there are two virtual machines and multiple zones. So we're across zones 1, 2, and 3. If we click on the first instance in the scale set, we'll see that that's in zone 3. If we go back to our instances and we click on the second instance in the scale set, we'll see that that's in zone 1. So our application is distributed across two availability zones within Azure. Now, if we go to scaling, you can see that I've got a rule here that is we're going to scale based on a metric. And you can see that when the message count is more than 10 in a queue called TWT queue, we're going to increase the instance count by 1. So hopefully if we go and add some messages to that queue, we should see this virtual machine scale set scale out based on the queue length. So if I head over to my storage account, I'll filter based on the TWT name for Tailwind Traders. I'll pick on my specific subscription so we can filter that. You'll see that I've got a storage account there, and then within that storage account we're going to click on queues. And then you see we have a queue called TWT queue. If we click into that, there are currently no results. There are no items sitting in the queue at the moment. Now what we're going to do, we're going to go ahead and start adding some messages into that queue. So I wrote a small bash script that goes ahead and adds some messages to the queue. We're going to be leveraging the Azure Cloud Shell here to be able to run that script. If you're not aware, the Azure Cloud Shell gives us the ability to use a terminal environment against our Azure environment. So it's a really nice way for us to interact with our Azure environment right here within the Azure portal. So here you can see I've run that script called add to queue. It's first going to go and see how many resources in the scale set. We've got 2 instances, and now you can see that I'm adding more and more messages to the queue. If we go and refresh our TWT queue, you can see all of those messages saying hello Ignite the Tour are populating into the queue. We're going to let some of those messages go into the queue and go over to our instances. We'll refresh that and see if there's anything there yet. And yet, as you can see, as we reach more than 10, we've got extra instances being added to our scale set. We've got to 20, so it's actually added 2 instances, and it will continue to add more instances there. You see at the end here that now we've got 4 instances in our virtual machine scale set, 2 of those being created. So that's how we can decouple our application leveraging queues and have our scale set scale based on the number of items that are in the queue. A really simple way to make our system much more scalable by decoupling via queues. Another way that we can improve the performance of our application is to implement an in-memory cache. Now, I know that performance does not equal scalability exactly, but by improving the performance of our application, we can reduce the load on other resources, meaning we hopefully don't have to scale as soon. Azure Cache for Redis is a managed Redis offering in Azure. It can be used for a number of patterns or use cases. For our product service, we would likely implement the cache aside pattern, which means we would load items from the database into the cache as needed, making our application more performant and reducing the load on the database. Redis can also be used as a messaging queue for caching web content or for user session caching. These use cases may be more suitable for other parts of our Tailwind Traders system, such as the shopping cart service, where we can store the shopping cart data per session in Redis, as opposed to in a cookie or a persistent database. So now that we've made our compute more scalable, let's take a look at that database. We're using Azure SQL Database here, which means it's a managed SQL server offering from Azure. As relational databases are much harder to scale out than non-relational databases, the first thing we should probably do in order to scale our database is to scale up the size of the database. This can be done very easily with Azure SQL via a simple API call or even a slider in the portal with an average downtime of under 4 seconds. If this doesn't meet our requirements, depending on our traffic characteristics, it may be more suitable to scale out the reads to the database. With Azure SQL, if you're using the premium or business critical tiers, read scale out is enabled by default. In fact, you can't even enable it on the basic or standard tiers. This would enable us to route read traffic to our read replica. This will have to be implemented in code though, so let's have a look at how we could do that. Within your application logic, you simply update the application intent attributes in your database connection string to reflect which server you wish to connect to. You choose read only if you want to connect to the replica, or read write if you want to connect to the master. Now, as this needs to be implemented in code, it might not be a suitable solution. What if every single product service needs the ability to read and write? Well, then you're not going to get much benefit from read replicas, so it does depend on the traffic characteristics of your application. In that case where we can't use read replicas, we need to look at scaling out SQLDB by sharding. Sharding is a technique to distribute large amounts of identically structured data across a number of independent databases. Sharding might be required for a number of reasons. It could be that the total amount of data is too large to fit within the constraints of an individual database. It could be that the transaction throughput of our overall workload exceeds the capabilities of an individual database. And lastly, less of a scaling reason, but there may be a requirement that separate tenants need to reside on different physical databases, potentially for compliance reasons. In this case, our application would then add the relevant data to the relevant shard, and therefore make our system more scalable beyond the constraints of an individual database. Now, this may seem pretty complicated, and it can be, but if you're using Azure SQL, we offer a set of tools called the Azure Elastic Database tools, which have a number of tools for creating, maintaining, and querying sharded SQL databases in Azure from your application logic. So it makes it a lot easier. So what's next? We've taken our product service, we've scaled the compute, we've made it more available in the process. We've also added Azure Cache for Redis to improve our performance. We've decoupled via queues, and we've scaled out our Azure SQL database via sharding to meet all of the scalability requirements that we might have as Tailwind Traders. The next step as Tailwind Traders business goes from strength to strength might be to go global. But I just want you to take some considerations into account before trying to implement a completely global architecture. The first question is, do you really need to go global? We need to understand what pain our customers have before taking on such a task. Can we maybe get the content closer to our end users via a content delivery network? Do we really need to scale one system across two geographies? Does a US user need to have the exact same account in the UK? It might be acceptable to have two independent systems, one in the US and one in the UK, for example. This might be acceptable. It's a very common pattern in the e-commerce world, actually. And then leaning on the independent system question, if we really do need a globally distributed system, what consistency do we need for the database? Strong consistency of our data across the globe is very, very difficult to get right. And in some services like Cosmos DB, it's not permitted, literally due to things like the speed of light. So some things to bear in mind there before you decide to go global. So after reviewing our costs, understanding our limits, and whether we need to manually scale anything, as well as re-architecting our services to be more scalable and reliable, we'll hopefully be able to remove these single points of failure, be aware of our pre-provisioned limits, and know what our costs are going to be, so we can survive the launch of the electric hammer. So to summarize what we spoke about in this session, first of all, for planning for growth, are you aware of what your service limits are? Do you know when you're going to hit them? Could you plan for scale using capacity planning? Do you know what your resource usage is now and in the future? And could you predict what your future cloud spend is? When you need to scale, could you leverage an inherently scalable service instead of the one you're already using? Could you leverage something like Azure Storage instead of running your data on a virtual machine yourself? Should we fix the bugs or add more resources to the problem? Those questions that I asked earlier before we go about scaling our system. Are you able to scale horizontally? Do you meet the requirements for that? Can you decouple your system using queues? Can you make things more independently scalable based on metrics that matter to the independent services? And will caching help? Can that improve performance before you need to throw more resources at your database? And from a reliability perspective, as this is a reliability learning path really, are you leveraging availability zones for reliability? And do you really need to go global? How reliable will your system be if you're dependent on cross-globe consistency of your data? These are all good questions to ask yourself when you're reviewing your systems and planning for future growth. So just to give you some heads up, here's a link to some relevant docs and some more learning following this session, particularly the Azure Architecture Center. And if you want to get practical with learning Azure architecture, head over to Microsoft Learn. There's a great learning path on architecting great solutions in Azure to help you understand how to architect solutions in Azure. And go ahead and get the Azure Certified Solutions Architect certificate. You can go ahead and check that out at the link below. In fact, actually, with this QR code here, you will get a free certification exam to all people that attend this event. So you can take advantage of this for any fundamentals or role-based certifications. It's up for this is valid for 6 months post this event. And lastly, there's that picture slide again in case you didn't get a chance at the beginning. Some session resources there, particularly for this session. All of the code and samples on GitHub for the demos that you saw, and all event resources are there for the entire event at the link below. Thank you very much for coming along to this session here in Orlando. It's been great having this conversation with you. Thank you very much.